course will cover thermodynamics in equilibrium. Okay, we'll talk more about what equilibrium is, and the topics included in this course are zeroth law of thermodynamics, that will give us the definition of temperature. We'll talk about first law of thermodynamics, that will introduce the meaning of heat and work. We'll talk about second law of thermodynamics, which will give us the idea about entropy. And then we'll talk about third law of thermodynamics, which is basically the behavior of substances at low temperature. We'll also see lots of equation of states that describe the thermodynamic state or behavior of system. We'll also learn about representing the relationships between different thermodynamic variables such as temperature, pressure, volume, number of atoms or molecules. And then we'll also talk about Maxwell's thermodynamic relations. Okay, that will give us the tools to relate different variables. And then we talk about heat engines, okay, something like Carnot cycle. So these are the basic topics or general topics that we will be covering in this course. Okay, so let's talk a little bit about some historical background on thermodynamics. So the development of thermodynamics began at the start of Industrial Revolution. Okay, and the experiments of Joule, Hearn, and other scientists, as well as the theoretical study of Helmholtz's results, resulted in the principle of conservation of energy. So there is principle of conservation of energy in mechanics, which we talked in introductory physics, and there is also conservation of energy in thermodynamics. Okay, so the conservation of energy of thermodynamics is basically relation between work and energy. Okay, what happens when you apply some work, what happens to the internal energy of the system, okay, and what happens to the temperature, all those kinds of things. So we'll talk about that in the coming chapters. And then Sadi-Carnot in 1824 gave Carnot's theorem that led to second law of thermodynamics. Okay, so Carnot's theorem is one of the foundation of thermodynamics. It gives us way to construct engines that have the maximum efficiency. And then Clapeyron put the Carnot's theorem into mathematical form. And Clausius and William Thomas, who later changed the name to Lord Kelvin, gave the concept of entropy. And then Nernst and Planck, actually this is not Planck, so Nernst and Planck they gave the third law of thermodynamics, which basically deals with the entropy or behavior of system at low temperatures. So all of these things are study of thermodynamics at macroscopic level. And then later Boltzmann gave us a way to study thermodynamics on molecular basis, okay, through or by using statistical thermodynamics. So Boltzmann gave us a way to understand the macroscopic world, such as what happens to the temperature, volume, or pressure using statistical approach. Okay, so let's talk about thermodynamics. So what is thermodynamics? So thermodynamics is the branch of physics which is mainly concerned with the transformation of heat into mechanical energy. Okay, it involves the study of interaction of one body with another body, the interaction being described in terms of quantities of heat and work. Thermodynamics can be defined as the study of equilibrium properties in which temperature is an important variable. Also, in thermodynamics we study relationships among the state variables describing a thermodynamic system. Okay, state variables means the variables that define a particular state of the system. For example, in introductory physics, if you throw an object in air at a particular instant of time, its state can be defined by its velocity, position, okay, those kinds of things. Likewise here in thermodynamics we can define the state of system by using pressure, volume, temperature, those kinds of things. So we'll talk about the relationships among those state variables. Okay, so let's talk about some common terminologies that we often use in thermodynamics. So you will need to know all these terminologies because we'll be using these terminologies quite often in this course. Okay, throughout this course these terminologies will be used again and again, so you need to understand what each of these terminologies are. So the first one is system. So what is system? So system is a definite quantity of matter bounded by some closed surface. Okay. For example, a gas contained in a cylinder with a movable piston is a system. So you have a cylinder with some movable piston. Movable piston means you can move this piston up or down, and this is filled with some gas. Okay, so that's the system. Another example of system is a tire containing some air. Okay, you have tire with some air, so this tire containing air is a system. Surrounding. So what's surrounding? A system may exchange energy with other system, which constitutes the surrounding of the given system. So let's say we have atmosphere outside, and if this is not completely insulated, then this system, the gas in this system can exchange energy as well as matter, okay, with the outer system or outer part. So for this system, for this piston system, this outer air or outer molecules comprise the surrounding. Okay, so this is the surrounding for this system. Another example is, let's say you have a container that has some kind of partition. Okay, so you have on left side chamber A, on the right side you have chamber B. So A is filled with some gas and B is also filled with some gas. So you can call this A as system A, and for system A this B would be the surrounding. Okay, so this would be surrounding for system A. Likewise, you can call B as a system, system B, but for system B, A would be the surrounding. Okay, so anything that is outside the boundary of the system is surrounding. And then the next thing is universe. So what's universe? So when we combine system and surrounding, the totality is called a universe. So in this case, this whole thing is the universe. Okay, here in this case, this thing, system with the piston containing the gas and outer atmosphere comprise a universe. The next thing is open system. So we talked about system. So what is open system? Open system is a system which can exchange both matter and energy with its surrounding. So like I said before, let's say we have some kind of universe. So this is universe, and there is a partition, and it has system A and system B. Okay, so for system A, this is the surrounding, and let's say this wall is a kind of wall through which there can be exchange of particles. Okay, so particles from here can go through that wall to this system, and the particles from B can go to this side. Okay, so there is exchange of energy, exchange of particles between A and B. Also, there can be exchange of energy between A and B. If both particles as well as energy can exchange between A and B, then the system is called open system. Okay, so in this case, A is an open system and B is also an open system. For A, B is the surrounding. For B, A is the surrounding. Closed system. So let's say we have a partition which doesn't allow the exchange of matter through it. That means the particles from A cannot enter B through the partition. Okay, so or B, the particles in the B cannot move towards A through the partition. So that means this partition is impermeable. Okay, but it can transmit, it can pass energy through it. Okay, although it cannot pass particles or matter, but still it can pass energy. In that case, we can call A to be a closed system. In closed system, this system can exchange energy with another system or surrounding, but there is no exchange of particles. So particles cannot escape out of the system. Isolated system. Isolated system is the system in which neither matter nor energy can escape the system. Okay, so or enter the system, not just escape, but it cannot also enter the system. So there is no exchange of matter or energy between the system and surrounding. So the next terminology that we often use in thermodynamics is thermodynamic variables or properties. So thermodynamic variables are the variables or quantities that describe the macroscopic behavior of a system, like I already told before. So we can describe the macroscopic behavior of a system by using pressure, volume, temperature, number, okay, all these kinds of things. So these are the thermodynamic variables or properties of a system. So the next common terminology we often use in thermodynamics is state variables. State variables are those variables whose differentials are exact. So what that means is, let's say we have some variable, say z, that is function of x and y. Then we can write the small change in this z as the linear combination of the change in x and change in y. What that means is, if you have, let's say, some point x, some point z on this xy plane, okay, so if you want to find small change in this z, then you can find this change as the linear combination of small change in x, okay, some coefficient, small change in x plus some coefficient, small change in y. Okay, so that's how we can express this change. So basically this dz, or change in z, is the linear combination of change in x and change in y. Now this dz would be exact if it satisfies these three conditions. Okay, so those three conditions are, first one is if the partial of m with respect to y is equal to the partial of n with respect to x. Okay, the second condition for dz to be exact is the integral over a closed loop, the integral of z over dz over a closed loop is 0. Okay, that means if you integrate dz over some closed loop starting from a point and then come back to the same point, if you take the integral around this path, then if it is 0, then it's exact. Okay, the third one is the integral of dz from point A to point B is path independent, meaning if you take the integral of dz along this path, okay, meaning you add these small differentials along this path, you get the exactly same value if you do the same integral along some other path. Okay, or you can do the integral along some other path, you get the same value. Okay, so this integral is path independent. If the differential satisfy all these three conditions, then this dz is exact. If dz is exact, then z is a state variable. For example, pressure, volume, and temperature are state variables. So the next terminology that we often use in thermodynamics is extensive properties. Okay, so the extensive property is the property that depends on mass or scale of a system. For example, volume. So what that means is, if you have let's say 1 kilogram of some volume, 1 kilogram of object that has volume V, and you have another 1 kilogram that has volume V. Now if you add these two, then you will get 2V. Okay, so your volume will increase to 2V. So if there is increase in the scale when we increase the mass, then it's called extensive property. Okay, and there is also property called intensive property, which do not depend on mass or scale of a system. For example, let's say you have 1 kilogram of a substance that is at temperature T, and we have another 1 kilogram of a substance, same substance, that has temperature, let's say T. Okay. If we add these two samples, the resultant will have temperature T. The temperatures won't add up. Okay, you won't get 2T. The temperature will still be T. So those kinds of properties that do not depend on the mass or the scale is called intensity properties. Okay. Another example is pressure. Okay. So for example, you have pressure of 1 kilogram of sample is, let's say, 2 pascals, and you have another 1 kilogram of a substance that has the same pressure, 2 pascal. Now if you add these two, if you increase the scale or if you increase the mass, you have now 2 kilogram. You also increase the volume, but you will still have the same pressure. Okay, so pressure is intensive property. You do not increase the pressure by adding the mass. Likewise, density, you have a piece of copper or something, okay, or gold. So this gold has, let's say, a mass of 2 kilogram. You cut this gold into half, so you have 1 kilogram of gold on left and 1 kilogram on right. So you will still have the same density as this original gold. Okay, the density won't change by cutting the gold into half. So intensity property is the intrinsic property of an object or a system. So let's look at the next one. The next one is thermodynamic state. So thermodynamic state is defined as a condition that is uniquely specified by a set of properties, for example, pressure, volume, and temperature. Okay. So what that is let's say you have a cylinder with some gas, okay, and it is enclosed by this piston. So let's say initially the gas has pressure P, volume V, and temperature T. So this is one state of this system. Okay. Now let's say you change the volume, okay, by pulling this up, and when you pull it up, now these variables will change. Okay, now you will have P, let's call this P1, V1, and T1, and you will have P2, V2, and T2. So this is another state. Okay, if you pull it up again, now you will get a third set of variables, or third set of values I should say. So P3, V3, T3. Okay. So each of these are unique states. Okay. Just like in introductory physics, if you throw an object in air, so at each and every point along this path, it will have a specific set of position, velocity, okay, or acceleration, x1 v1 a1, x1 v1 a1. In the thermodynamic system also you can have different sets of coordinates, I should say coordinates, along the process. So you are going through some process here, like you're pulling it up, and you'll have different sets of coordinates for different instances. So those states are called thermodynamic states. So next thing is equation of state. This is very important for thermodynamics. So in order to describe the thermodynamic state of the system, which we just described, we need certain variables, like here in this case we are using PV and T to describe the state of a system. Okay, and those variables in general are mechanical variables supplemented by the thermal state of the system. Okay, so for example, the thermodynamic state of a gaseous state or gaseous system can be specified by its pressure, volume and temperature, just like we described. But out of the three variables PV and T, only two are independent variables, and the third may be considered as their function. What that means is you can write the third one, let's say in this case temperature, as the function of P and V, or you can write pressure as function of V and T. Okay, or volume can be written as the function of P and V. Okay, so you have two independent variables and the third one is the dependent variable, meaning the third one depends on how you change the other two. So the equation concerning the pressure, the volume and the absolute temperature, so this is in terms of Kelvin scale, which we call absolute temperature. We'll talk about that in the next topic. So the equation concerning the pressure, volume and absolute temperature of a system is what is called the equation of state. Okay, so for a gas forming the system, so these three quantities are not independent, just like I said, so they are not independent. So, and they are connected by some kind of relationship, okay, given by some equation. So like you might have seen this equation before, so they may be connected by some kind of equation like this. So PV is equal to nRT. Okay, so there is some kind of relationship between the three variables. So we can write this relationship. This is just an example. We can have a different kind of relationship also. I'm just giving a very basic example that shows the relationship between PV and T. Okay, so we can write the relationship between the three variables as this equation. So in terms of function, so PV T is equal to 0. So that's that. Okay, so the general form of that, and this equation is what we call equation of state. Now let's talk about thermodynamic equilibrium. It's a very, very important concept. So if an isolated system is left to itself, the pressure and temperature at a given point approach to a steady value with the passage of time. And when these quantities have attained a steady value, the system is said to be in state of thermodynamic equilibrium. Okay. In such a system, the temperature, pressure and other thermodynamic variables of a homogeneous system are the same at all the points. So meaning, if you pull this like this one has some gas in it, So it is in the state of P1, V1 and T1. So you pulled it up, okay, and then you waited for a couple seconds or some instant, some time. Then after some time it will attain some equilibrium state. The meaning of that is it will have same value of P, V and T at each and every point. Okay, so there won't be any difference in the value of P, V and T in the system. It's same everywhere, and that's what the equilibrium is. So a system in thermomechanical and chemical equilibrium is said to be in thermodynamic equilibrium. So thermodynamic equilibrium means it's the combination of three types of equilibrium. So they are mechanical equilibrium, okay, and thermal equilibrium, and chemical equilibrium. Okay. So the next thing is thermodynamic process. So like I said before, we have some kind of system that has the thermodynamic variables P, V and T, or you can say P1, V1 and T1, and when we do something to the system that changes the values of those variables, then the something that we do to the system is called the process, okay, thermodynamic process. So that means thermodynamic process is any change which causes the thermodynamic variable of a system have new set of values. So when we go through a process, a thermodynamic process, we change the values of P1, P, V and T from say P1, V1 and T1 to a new set of values P2, V2 and T2. And by the way, I didn't explain that in the previous terminology. So I talked about mechanical equilibrium, thermal equilibrium and chemical equilibrium. So mechanical equilibrium means when the system is in mechanical equilibrium, its pressure is same everywhere, okay, at each and every point on this system. No matter where you measure the pressure, here, 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 you get the same pressure. So that means this system is in mechanical equilibrium. Thermal equilibrium, if you measure temperature at each and every point on this system, so that's the thermal equilibrium. And chemical equilibrium is, we'll talk more about this chemical equilibrium later. So we can say it's homogeneous everywhere, okay. It has the same constituent everywhere. If you mix 2 or 3 types of gas, so you will have same kind of homogeneous mixture everywhere in that system. So that's the chemical equilibrium. And there is also more about chemical equilibrium which we'll talk later, okay. We'll have something called chemical potential. So chemical potential would be same everywhere when it's in chemical equilibrium. Okay, so next thing is reversible process. What is reversible process? So if a process can be carried out in such a way that the effect produced by it on the system as well as the surrounding can be completely restored to its initial states and no changes are left in any of the systems taking part in the process or in the surroundings, the process is said to be a reversible process. Okay, so in a reversible process, the system passes through a succession of equilibrium states or states that differ from equilibrium only infinitesimally. Such a process must take place slowly in a controlled manner. If a process does not satisfy these conditions, then it is irreversible. Okay. So that means if you have a system in some state P1, V1 and T1 and you pull it up, let's say you pull the piston up, so now it will be in a different state, so P2, V2 and T2. Now if you could somehow take it back to the same state P1, V1 and T1, then this kind of process is called reversible process. Okay, so in order for you to take it back to the same state, you will need to carry out the process, the initial process in very small steps. Okay, if you pull it really rapidly, then you will create some gradient here, so that means this system won't be in equilibrium. So when it goes out of the equilibrium, then you won't be able to bring it back to the same state. So that's why when you pull it up, you need to pull it very, very slowly, so that you give some time to have the same values or equilibrium state in all the different parts of this system. Okay, so when you do it rapidly, you will have some set of values at this point and some set of values at that point, some set of values at that point, some set of values at that point. So then this system won't be in equilibrium, and if you want to take it back to the same system, then that won't be possible. That's why you need to do it very slowly, so that at each and every point you have same values of the thermodynamic variables at each and every point in that system. So again, irreversible process is the process that cannot restore the initial state of the system. You cannot take back to its to the initial state. So that's the irreversible process. Quasi-static process. So in quasi-static process, the deviation from thermodynamic equilibrium is very, very small. Okay, so there is a little bit of deviation, but it's negligible. So all the states through which the system passes through a quasi-static process may be treated as equilibrium state. So when you go from one state to another state in a small step, you pull it very, very little by very small amount, then during that time there would be a little bit of variation in the thermodynamic variables in this system. Okay, so meaning if you measure the temperature here, the temperature here may be slightly different from the temperature here, it would be slightly different from temperature here, but the difference would be negligible. Okay, so that we can just neglect that, we can just consider that the temperature is same everywhere. So that's this small step is what we call quasi-static process, where the equilibrium is maintained. Okay, there's a little bit of deviation, but we can still consider that it's still in equilibrium. The next one is isothermal process. So what is isothermal process? So if a thermodynamic system is perfectly conducting to the surrounding, and it undergoes a physical process in such a way that its temperature remains constant throughout. The process is called isothermal process. So you can have a cylinder, but here this part or this part that are in contact with the surrounding are conducting. Okay, so they can conduct heat through it. So in that case, there would be some exchange of heat which will change the temperature of this system, so that the process in which the temperature change or the temperature changes is called isothermal process. The next one is adiabatic process. Adiabatic process. So adiabatic process is the process in which the system does not exchange heat with the surrounding. So this is perfectly insulated, not conducting. So in case of adiabatic process, this is insulated. So when you do something with the system, it doesn't exchange heat with the system. So the process is then called adiabatic process, and this wall is also called adiabatic wall. Adiabatic wall. Isobaric process is the process in which you keep the volume constant. Let's say you have a enclosed container. Okay, there is no or okay, you can just consider this one. So you heat this in such a way that you do not move this. Okay, you fix this. If you fix this, the volume of the gas will remain the same. Okay, and the process would be called isobaric process. So when you do something with the system where you keep the volume constant, it's the isobaric process. Isochroic process is the process in which you keep the pressure of the system constant. Okay, so we'll talk about all these things in the next chapter. So these are the common terms that we'll be using very often in this course. So I would highly recommend you to review these topics, read the book, and then make sure you understand all these topics. Okay, so if you have any question, any problem, please come and talk with me. I will be happy to answer the questions. So that's all for this lecture. We'll continue this in the next lecture.